All right, what I'd like to do today is to finish up on reliability to enable you to complete homework number 10 successfully. And if you'll recall, reliability is necessary for validity, reliability is repeatability, and we have two ways we can calculate it. We can use what's called the interclass correlation coefficient or the intra-class correlation coefficient. When we calculate an interclass correlation coefficient, we're simply calculating a Pearson R. In the case of the intra-class correlation coefficient, which is indicated as ICC, you use a repeated measures ANOVA as the statistical approach. Either way you do this, you're going to end up with a number between 0 and 1, and certainly this is the best way that we can have a measure of how much retest reliability we have. If a test was perfectly reliable, we'd have a value of 1. If a test is not reliable at all, we'd have a value of 0. So the Pearson R is the interclass correlation coefficient. The repeated measures ANOVA is used to establish the ICC, or the intraclass correlation coefficient. All right, let's just talk about the two types of reliability now. There's relative reliability and absolute reliability. With relative reliability, you are getting kind of a measure of the degree to which individuals maintain their position or rank in a sample over repeated measurements. So you test people twice, and you see, were people who scored high on the first trial, high on the second trial? Or people who scored low on the first trial, low on the second trial? This is what we call relative reliability, and this is what we usually see reported in research articles that document the reliability of a test. This graphic comes from the optional reading in the journal Physiotherapy, and it shows you an example of good reliability on the top, poor reliability on the bottom. What you see here is the greater the reliability, the higher the Pearson R, okay, relative to something that's not as reliable. And in tests that are reliable, people maintain their relative position or rank in the group. A person that is high on the first trial is still high on the second trial. A person that is low on the first trial is low on the second trial. So you see that relative reliability, as assessed using the Pearson R in this case, is pretty high. People maintain their relative position in the group, as compared to this test, in which people who are high on the first trial aren't the highest on the second trial, and you don't have as great a reliability coefficient. So this is relative reliability. We can establish that using the Pearson R. We can also use the ICC, or the intraclass correlation coefficient. It kind of gives you an idea of where in the group are you positioned as you go from trial 1 to trial 2 of the test. Okay, now here's an example where we compute reliability. We have 10 people. We had them do sit-ups once, trial 1, and we had 10 people repeat. They did sit-ups once again. That's trial 2. We can then calculate the Pearson R, which in this case we're going to indicate as an Rx x prime, to indicate that we're correlating the same thing to itself instead of an x to a y. And we see we have pretty high reliability here. Once you calculate this reliability, you can then interpret it, should you want to, relevant to reliability theory by saying our correlation coefficient was 0.927, so 92.7% of the observed score variance is true score variance for this sit-up test. Okay, so there's a bunch of problems when we use the Pearson R as opposed to the ICC using repeated measures ANOVA to compute the reliability coefficient. As we learned before, the PPMCC is technically a bivariate statistic. It's an X and Y statistic, and that's really not appropriate technically when you're correlating something to itself. In other words, an X to an X instead of an X to a Y. So the Pearson R technically is probably not the best statistic to use in determining reliability. The other problem or limitation of using the Pearson R for reliability is you can only have 2 trials, not more. Okay? So if I wanted to test the intake of calcium for a group of young girls, I'd go to their house, I ask them what they ate, I compute the calcium intake. It's going to be variable over a number of days. And I'd be interested in the reliability of multiple trials, not just 2 trials. So the Pearson R is not going to be appropriate for that, whereas the repeated measures ANOVA will be. But mostly important, and you notice that I've put a lot of stars on this slide, is this limitation of the Pearson R, okay? In the instance that you see that's illustrated in this slide, here are the person's scores as we go from trial 1 to trial 2. And you'll notice that there's a constant change in the measures. In this case, each person is improving by a score of 10 as we go from trial 1 to trial 2. Trial 1 to trial 2. The problem is, and you can try this on your own, I encourage you to do it on your calculator or with Excel. If you were to calculate the reliability coefficient, simply the Pearson R, relating these scores to these scores, when there's a constant change in measures like this, all the points are on a line. So you end up with what you appears to be perfect reliability. But it's very deceiving, because we see here that the mean, in fact, changed quite a bit. And these aren't consistent scores as we go from trial 1 to trial 2. In fact, there's been a systematic increase in the number of push-ups, let's say, that someone was able to do as we went to the second trial. So the Pearson R can be misleading in this sense. Watch out for it. It's one of the main reasons why we choose to report most reliabilities as the ICC. Notice my cursor at the bottom here. It's the intra-class correlation coefficient, and you can see the range that is reported for some of these tests, and pull-ups tests, volley tests. These are mostly acceptable reliability coefficients because they're above the 0.8 that we usually use in our field in determining acceptable reliability. We need reliability to be high to have good validity. You got to memorize this, you got to understand it, and generally, again, we're going to want reliability coefficients above 0.8. All right, so a little aside here, I know that in your careers you're going to be encountering situations in which you do test more than once. You have what we call a multiple trial test. For example, you pinch, and you pinch on a skin fold measure. Or you give the 40-yard dash trial twice. Do you use the best, or do you use the mean score in actually giving that person a number? Well, there's some good general guidelines on this. First of all, you look at the test manual and you follow the convention of the test manual from whoever described that test originally. But in general, if we're interested in maximal possible performance, you're going to take the best score. If you're really interested in true ability, okay, remember that we're going to have random error that's going to have some high scores, some low scores. Truth is kind of in the center somewhere when we have this random error, and therefore, for many of the tests that we do in our field, we're going to use the average or the mean score. So you're going to have to know for a test, do you use the best score or do you use the mean score? And these are some good guidelines for you to follow. So what do you think you'd do in these situations? I would take the mean of the skin folds. What would you do in this situation? This is a performance test. I would use this score because it indicates the fastest or the best trial. Okay. Absolute reliability is the other type of reliability. It's a little bit different than relative reliability, where we were determining how you maintained your position in the group. Instead, what you're going to see here is the absolute reliability is the degree to which repeated measures vary for individuals. So if I were to measure Brandon or Luis's height 1,000 times, right? You know that what's going to happen is sometimes they're going to be a little taller, sometimes a little bit shorter, but it's going to center around some mean there. And the way we capture how much error is involved with this random error for a person who's measured repeatedly over and over and over again 1,000, 10,000 times is we use what is called the SEM. The SEM is the standard error of measurement, and there are other absolute reliability indices that you might see in some research reports, including the coefficient of variation and the Bland-Altman's 95% limits of agreement. But we use the SEM sometimes. It's not as reported quite as often as our field as relative reliability values, but it's easy to calculate or estimate, and this is what it is. It's error, so we want error to be minimized. Okay, that's the first thing to take note of. And the next thing is that it reflects the standard deviation for the distribution of measures for an individually repeatedly measured. So again, I take your height once, I take your height twice, I take your height 1,000, 1,000,000 times. What's the standard deviation, all right, of those measures? Okay, that's what is the standard error of measurement, or what is called the SEM. Turns out we don't want to measure you 10,000 times, so we can estimate this error using data from the whole group and the formula that's shown on page 102 of your book and is reproduced for you here. This is the standard error of measurement. It's an absolute reliability index, and what we do is we take the standard deviation for the test. We take that times the square root of 1 minus the correlation coefficient, okay? The correlation coefficient or reliability coefficient. And we interpret this like other error. Again, truth is probably somewhere in here. Sometimes we measure you taller or shorter than truth. We hope that this error is minimized, all right, that in sense there's a very narrow normal curve, if you will. But once you calculate the standard error of measurement, you interpret it like this, and I bet you're going to guess what this says. 68%, okay? You recognize that number. There's a 68% chance that the subject's true score is within plus or minus 1 standard error of measurement of the observed score, okay? So there's 95% chance that the subject's true score is within plus or minus 2 standard error of measurements of the observed score. Okay, we don't use it as often in our field, but you should be familiar with it. Here's the formula for it. Here's the interpretation. You have a problem like this in your homework assignment. So, quick review. The standard error of measurement is a reliability measure. It is a reliability measure, and it's going to tell us how much error is involved as you repeatedly test someone over and over and over again using the same test, okay? And the formula is shown here. That's a little different than something that we did before, which was the standard error of the estimate. And I'm going to remind you that that's a number, the SEE, which is going to tell us about the accuracy or the validity of a test. So the SEM, reliability, the SEE is a validity coefficient. Okay, I hope you know what reliability and validity are. I hope you know that we're interested in hitting the target. We can't do validity and get a truth unless we have repeatable measures, okay? If we want truth, it needs to be valid, so it must be reliable, and it must be relevant, okay? How do you compute the reliability coefficient? You can simply use the Pearson R. When you use the Pearson R, or the interclass correlation coefficient, okay, you compute the PPMCC, okay, but there's 3 major problems with that. So oftentimes, we are going to report reliability as the ICC determined via repeated measures ANOVA, or just simply ANOVA, okay? Here's an example of kind of what you want to see. You give a leg press twice. Hopefully the scores will be positively correlated and close to the line. All right? Our line of identity says, hey, if you had 100 here, that would be 100 here. So that's where we want the line to be. It's a little bit off, but this is pretty decent reliability on something of a maximal leg press test that you might give. You know how to report these things using SPSS. You simply use the Pearson R. Is this acceptable reliability? I would say yes. I would say yes. Why? Because it's above that 0.80 that we usually use in our field as an acceptable reliability coefficient. Okay, these last couple of slides get you to think about how reliability would be influenced by, you know, you had a restriction of range in a bunch of high caliber Olympic athletes. The correlation coefficient is going to be very low. So beware, you know, the scattergram for this is going to be a bunch of dots right up here. if we were talking about test, retest for a group of Olympic athletes, all right? So we may not be able to get a high reliability coefficient simply because you have a restriction in range of the values. Similarly, if you had old ladies and they were osteoarthritic and they come in and test, trial 1 to trial 2, we're going to have very poor reliability. We're going to have poor reliability because one day they come in and they say, oh, I'm doing great. Another day they say, oh, I got pains in my knees and my back. So they're not going to perform as well. These dots might be all over the place in an osteoarthritic older adult group. So how do we determine reliability? Once again, what you're going to do in that case is we are going to test 30 or more subjects. You're going to test them under controlled conditions to minimize error. You're going to calculate the ppm-cc or do repeated measures ANOVA, and then you're going to figure out, does it meet the 0.80 value that we consider acceptable. ICC, use repeated measures ANOVA. It's beyond the scope of this course to show you how to do that, but you're going to see a lot of times in our field that these values are reported as the ICC. This slide shows you right from your book some of the values that are reported for the intraclass correlation coefficient for some tests. And all of these are, most of these are acceptable. You can see down here that I might not be inclined to give a test like a half-mile run to girls hoping to get a reliable test result simply because people can't replicate their performance as you go from trial 1 to trial 2. Okay, thank you. Really appreciate it.